this video, we want to graph this logarithmic function here and also give the domain and range of the function. Now in an earlier video, we found the inverse function of this logarithmic function, which turned out to be an exponential function. And I'll link the video to the in the description in case you missed it. So let's look at your typical graph for a log function with base larger than 1. In this case, the base is 2. If this were just a f of x or just y equal to log of just x to base 2, then the log of 0 is not defined. So this particular graph will have a vertical asymptote, which would turn out to be at the y-axis, or x equals 0. And notice that if x is equal to 1, the log of 1 to base 2, or any base for that matter, is going to be 0, because in this case 2 to 0 is 1. So this graph will have a vertical asymptote at x equals 0. It'll pass through 1, 0, and your typical graph with base larger than 1 will go out something like this. It'll go up like that. You add a number here to the right, plus 1, would simply move this graph up 1 unit. So it'd be, this point would go to up here 1 unit, and then it would still again go up. Obviously the x-intercept would change. Here it's at 1, 0. That's going to change when we do that. And this right here, x minus 2, shifts the graph 2 more units to the right. If this were a plus, it would shift it 2 units to the left. So if I say, what is the domain of this? Domain relates to x. That would be the set of all x, such that x is greater than 0. The range, you can see this goes down to infinity. It goes up to infinity. The range would be minus infinity to infinity. That's for this one here. Obviously, we want the information for this one over here. So let's go ahead and beat this. So let's suppose we want to find the x-intercept. So what's going to be the x-intercept to this graph? We kind of know what the graph is going to look like already. This is going to shift it 2 units over. This is just going to bring it up 1 unit. So we want the x-intercept, and the x-intercept is going to be obtained when the y is 0. So let's let, in this case it's f of x, so let's let that f equal to 0. And then we have the log base 2 of x minus 1, or x minus 2, rather, plus 1. So we're letting y be 0. Whatever we get for x will give us the intercept. So let's bring this 1 over, add negative 1 to both sides. So this will be a negative 1 here, equal to log the base 2 of x minus 1, x minus 2. And then we rewrite this as an exponential. So I'm going to just start with this side and say, okay, this, by definition, x minus 2 would have to equal to this base 2 taken to the value on the right, which would be the exponent. This would be negative 1, so this would be 2 to the negative 1, or 1/2. So this would tell me then that x is equal to 1/2. 2 to the negative 1 is 1/2. Add 2 to both sides, so this will give me a 2 here. Common denominator is 2, so multiply here by 2 and 2. I get 4 over 2, so that'll give me 5/2. So the x-intercept for this graph is 5/2. And notice, to find the y-intercept, you replace the x by 0. But if you replace the x by 0, you're going to get the log of negative 2. That's undefined. So that tells me that it does not have a y-intercept. Okay, so while we have this point, 5/2 and 0, and let's see if we can find another point here. We say, trying to find another point so that we had y equal to, let's plug in something here for x. That'll give us an exact answer. Let's see, if I put in a 6 there for x, that'll give me 6 minus 2, which is 4. And the log of 4 to base 2 is 2, because 2 squared is 4. So this then would give me 3. Okay, put a 6 there. 6 minus 2 is 4. The log of 4 to base 2 is 2, because 2 to the 4th is 4, and then 2 and 1 will give me 3. So the other point that I get then for this is 6 and 3. And then the other thing I know is that we have a vertical asymptote right here. This is 0 at 2. Put a 2 there, I get 2 minus 2 is 0. So I have, instead of a vertical asymptote at x equal to 0, I have it at x equal to 2. And remember, that's because the graph is going to shift 2 units to the right. So then basically the graph is going to look just like the one I had here a while ago of log of x to base 2, except it's going to move over 2 units, and it's going to cross at these points right here. So let's go down. There's your information. Vertical asymptote at x equal 2. The graph crosses at 6, 3, or has a point at 6, 3, and the x-intercept of the graph is 5/2 and 0. So let's come back over here then. This is what some of the information that I just went over. So the vertical asymptote, it's x equal 2, and the graph crosses the x-axis. The x-intercept is at 2 and 1/2, so it's this point right here. And again, it's going to have the same shape as the other one. It just shifts over a little bit, and it's also going to pass. The other point was 1, 2, 3, 4, 5, 6, and 3. going to be over here. So it's come down like this. So a little bit better here. It comes from down here and it goes out like that. And this point right here is the point 6 and 3. And this point right here is the point 5/2, 0. And you can see the domain from what we said earlier, and you can see it from the graph. The graph has to stay to the right of this line x equal 2. So I can say that the domain is, in interval notation, is 2 to infinity. So the graph stays to the right of this line. Now without the minus 2, it stays to the right of the line x equal to 0. So the domain there would be from 0 to infinity. And then of course the range, well, you can see it goes down this way. This is negative infinity over here, and it continues up. It goes up forever. So the range goes from the interval notation, negative infinity, to plus infinity. Now I mentioned that in an earlier video, this same logarithmic function, we found the inverse function. And I mentioned then that the logarithmic function and the exponential function are inverses of each other. So if you have the inverse of a logarithmic function, the ordered pairs of one, you reverse them, and you get the ordered pairs of the other one. So you have a log function, reverse the ordered pairs, those ordered pairs will be points on the graph of the inverse, and vice versa. So if I were to reverse, there's just these 2 points right here. Okay, so 5/2 and 0, so it will be 0, and 5/2 would be this point here, and then I reverse this point here, the 3, 6. So I go over 1, 2, 3, and say 6 up over here somewhere. And if I were to draw that graph, this point and that point, those would be inverses. This would be your f, of course, and this would be your f inverses, and they would be reflective over the line y equal x. So the line that I do here, that's equation y equal x, that's the line of symmetry. So you have an inverse function and the function, or a function and its inverse, and you reflect one or the other over this line of symmetry, it will coincide with the other part. But in this case, they wanted the graph of the main function. But I just wanted to illustrate that the log and the exponential function are inverses of each other. Again, the domain for this particular function is from 2 to infinity, and the range is from negative infinity to infinity. Thanks for watching. We'll see you next time.